I wish people understood that fundamental innovation today is paramount to having CDR be at the cost and scale it needs to be at in 5 to 15 years. Pushing the problem off until a later date is shooting ourselves in the foot in a meaningful way. My name is Mitch Rubin, Managing Director of Portfolio and Investments at Elemental Impact, and I'm excited about the Climate Tech Map. In early 2019, I read The Uninhabitable Earth by David Wallace Wells. And it was my first rude awakening to how much of a problem we have ahead of us with climate change. It was one of those overnight mentality shifts. I immediately knew I had to shift my career and focus my time and energy on finding ways to slow and hopefully reverse the effects of climate change. Less than a year later, in January 2020, I was getting my master's degree in sustainability management. And during that time, carbon dioxide removal was just starting to become something tangible. There were maybe 5 CDR companies when I was first researching the topic, and fast forward to now, there are likely 500 or more. Overshooting 1.5 degrees Celsius of global warming is inevitable, and recent global policy pullbacks are only slowing the speed by which we are decarbonizing. It will require us annually removing between 5 to 16 gigatons of CO2 by 2050, and we're nowhere close to sequestering what we need. CDR is essential, both now and into the future, to pull us back to a stable climate. Engineered carbon dioxide removal, or engineered CDR, refers to technologies and processes that actively capture CO2 from the atmosphere or ocean and store it in a way that prevents it from re-entering the atmosphere for centuries or longer. Unlike biological carbon removal, which relies on natural ecosystems like forests, crops, and soils to absorb carbon, and mineral carbon removal, which stores carbon in inorganic alkaline material like rocks, engineered solutions use human-made systems and often involve industrial-scale operations. For engineered CDR, the primary benefits are 1, its relatively durable sequestration of carbon, and 2, it's also significantly easier to measure, monitor, and verify the carbon dioxide that's been captured. Engineered CDR's biggest problem is it's very expensive, it's resource intensive, and the technologies are mostly unproven. We need new innovations to help lower the cost specifically of engineered CDR and meet the demand of buyers who require CDR to decarbonize their operations or meet certain commitments. This includes in the voluntary market for now, but eventually hitting price points needed for the compliance markets to participate as well. Innovating engineered CDR means finding ways to take CO2 out of the air and ocean and permanently storing it in places so it doesn't return to our atmosphere. One area for further innovation is the process of CO2 sequestration. Today, one of the main methods for sequestering CO2 is pumping it deep underground, which works well, but is expensive and can only be done in certain places. This method is ripe for innovation, with scientists and engineers experimenting with new technologies that efficiently turn gaseous CO2 into rock, improving underground storage designs or using new materials to trap it. There's a big near-term market opportunity for finding ways to take that captured CO2 and rather than bury it underground, instead use it productively. This includes storing it inside of materials that have an inherent value themselves, such as concrete and other building materials. Another method that is ripe for innovation is increasing energy efficiency within direct air capture systems. These systems suck CO2 out of the air, but require lots of energy in the process. Innovations to improve materials, make machine design smarter, and reuse heat so these systems need less power will be critical to scaling this method. Beyond making today's existing CDR methods better, there is a massive opportunity for creativity and innovation in finding the next horizons of engineered CDR. One moonshot is finding ways to build engineered carbon capture into existing air and water flows. Passive removal means capturing carbon dioxide using air and water that are already moving through everyday systems, instead of needing to build new machines just to move air around. For example, carbon capture can be added to ship exhaust, building ventilation systems, or industrial water cooling systems. Because these systems already move huge amounts of air and water, carbon can be captured continuously, without using much extra energy. While this idea is still experimental in certain domains, it could make carbon removal cheaper and easier to scale by quietly embedding it into the infrastructure we already use today. My advice is twofold. First, be willing to think outside the box. And then outside of that box. The best, most important inventions may not have even begun yet. Secondly, don't let the near-term issues and questions around carbon markets prevent you from focusing on CDR. This is one of the most inevitable, essential needs for our entire planet for the foreseeable future. The question of who will pay for it and how will be answered in due time. I wish everyone appreciated how much innovation has occurred in such a short amount of time. We are still in the top half of the first inning here. And I wish people understood that fundamental innovation today is paramount to having CDR be at the cost and scale it needs to be at in 5 to 15 years. Pushing the problem off until a later date is shooting ourselves in the foot in a meaningful way. The horizons of innovation for engineered CDR are just beginning to take shape. We'll need new technologies, some of which haven't even begun to be invented yet, to get to that full scale. But just like the entrepreneurs and scientists of yesterday, who trailblazed paths forward in the midst of big problems, so too will the innovators who build the future CDR solutions for our climate crisis.